Alright, let's go. Number 10. The hidden planet in the most famous star system in astronomy. To understand why this discovery is so unsettling, you have to understand what HR 8799 is. It sits about 133 light-years from Earth in the constellation Pegasus. In 2008, it became the first star system in history where astronomers directly imaged planets orbiting another star. Not detected by wobble, not detected by transit, actually photographed. 4 giant worlds, glowing in infrared, orbiting a young hot star. For 18 years, HR 8799 was the poster child of exoplanet astronomy. Textbooks used it, documentaries used it, every planetary scientist alive knew this system by heart. 4 planets labeled B, C, D, and E. That was the story. In July of 2026, that story ended. A team using NASA's James Webb Space Telescope, led by researchers at the University of California and the Space Telescope Science Institute, pointed the observatory at HR 8799 to study the atmospheres of the 4 known planets. What they found instead was a 5th world, sitting inside the innermost orbit, roughly the mass of Saturn, silent, cold, waiting. The reason it went undetected for 18 years is what stopped the researchers cold. This planet is unusually low in temperature for its orbital distance. Its infrared signature is nearly invisible. Its atmosphere lacks the standard clouds and reflective layers that make young giant planets shine. Every model of planetary formation says a Saturn-mass world at that distance from a hot young star should be bright, warm, and easy to detect. This one is none of those things. The researchers, in their published paper, are careful to describe this as a formation anomaly. They use words like unusual and unexpected. What they do not say, but what other astronomers have begun saying privately, is what this discovery implies for the rest of astronomy. If a Saturn-mass planet can hide in plain sight in the most photographed star system outside our solar system for 18 years, in an era when we thought we had directly imaged every large planet in that system, then a very uncomfortable follow-up question becomes unavoidable. How many worlds are we missing? Not just in HR 8799, in every star system we have surveyed, in every young stellar cluster we have imaged, in our own solar system, in the dark stretches beyond Neptune, in the Kuiper Belt, in the vast frozen zone we call the Oort cloud. How many planets are moving quietly through the darkness, cold enough and dim enough that no telescope on Earth has ever seen them? The current best estimate from the same team is troubling. They believe hundreds of undiscovered planets may be hiding in the outer regions of our own solar system alone, some of them potentially larger than Earth, some of them potentially closer than we have any reason to expect, and we have no reliable way to detect them, not until one of them crosses in front of a distant star, briefly dimming its light. And even then, only if we happen to be watching that exact star at that exact moment. The solar system we live in is not the solar system we mapped. The solar system we mapped is a small, illuminated fraction of a much larger and much darker structure. And the rest of it, whatever it contains, has been sitting there the whole time. Number 9. The object that entered our solar system carrying the wrong chemistry. On July 1st, 2025, a survey telescope in Chile called Atlas detected a small, fast-moving object entering our solar system. Its trajectory was immediately suspicious. It was not in orbit around the sun. It was passing through on a hyperbolic path, coming from interstellar space and heading back out again. It received the designation 3I/Atlas, only the 3rd interstellar object ever discovered, after Oumuamua in 2017 and Borisov in 2019. For over a year, every major observatory on Earth pointed instruments at this thing. The James Webb Space Telescope observed it. The Hubble Space Telescope observed it. Ground-based arrays across 4 continents observed it. The Very Large Telescope in Chile. The Keck Observatory in Hawaii. The Gran Telescopio in the Canary Islands. Nobody wanted to miss what this object was. And what they found is the reason astronomers stopped publishing casual updates and started publishing carefully worded academic papers. 3I/Atlas has a methane-to-water ratio approximately 11 times higher than any comet ever measured in our solar system. Not slightly higher, 11 times higher. Its carbon isotope ratios are wrong. Its deuterium concentration, the heavy form of hydrogen, does not match anything we have on record. Its dust composition, when analyzed by Webb's near-infrared spectrograph, contains organic molecules in ratios that do not appear in any known cometary body from our own neighborhood. Each of these measurements individually could be dismissed. Together, they point to a single, unavoidable conclusion. This object did not form in our solar system, and it did not form in any solar system similar to ours. It formed in a place profoundly colder than our own outer solar system, around a star profoundly different from our sun, under laws of chemistry that produce compositions our own protoplanetary disk never produced. 3I/Atlas is, in effect, a chemical postcard from another star system, from a world that no longer exists, orbiting a star that may have died billions of years ago, spinning through the galaxy for however long it took to reach us. And here is the part that nobody has said clearly in public. 3I/Atlas was moving on a trajectory that took it deep into our solar system. It passed through the neighborhood of every inner planet. It came within measurable distance of Earth's orbit, and nobody detected it until it was almost on top of us. We had roughly a year of warning. In a solar system that is billions of years old, that is nothing. Now consider the follow-up estimate. Astronomers currently believe that objects like 3I/Atlas enter our solar system regularly. Not once a century, not once a decade, possibly several times per year. Most of them are small enough or dark enough that our current survey capacity cannot detect them at all, which means, on any given day, one or more of these objects is quietly passing through the space we live in. Foreign material, from somewhere else, made of things our chemistry cannot fully identify, moving on trajectories we cannot predict, arriving with no warning, and leaving before we understand what we just saw. The solar system, in other words, is not a closed room. It is a highway, and we have almost no ability to see the traffic. Number 8. The metallic waves that appeared on Mars. On July 24, 2026, the European Space Agency released an image captured by the Mars Express orbiter that stopped planetary scientists in their tracks. The image, taken over a giant impact basin near the Martian equator, appears to show something that looks almost exactly like a set of metallic waves, smooth, rippled, arranged in a pattern too regular for natural erosion and too geometric for standard volcanic flow. For the first several hours after the image was released, before anyone in the ESA team could publish an interpretation, the internet did what the internet always does: speculation, screenshots, whispers of alien architecture. Some prominent commentators suggested it looked like the wreckage of something manufactured. Others compared it to structures on Earth that are known to be artificial. But the real explanation, when it finally came, was in some ways stranger than aliens would have been. What the orbiter captured is the aftermath of a process nobody had documented at this scale before. Under the specific atmospheric pressure of Mars, which is less than 1% of Earth's atmosphere, iron-rich dust behaves in ways that are physically impossible on Earth. In extreme cold and near-vacuum conditions, iron dust can enter a state that behaves like a slow-moving liquid metal. Not liquid enough to flow like water, just liquid enough to freeze mid-motion, capturing whatever pattern it was in at the moment of freezing, and staying locked in that position for potentially millions of years. Which sounds academic until you consider what it implies. If iron-rich dust can behave this way on Mars, and if that dust gets regularly kicked up during the planet's periodic global dust storms, then Mars may be quietly reshaping its own surface on an ongoing basis, in ways we have been missing every single time we looked away. Which raises the question the ESA team asked, very carefully, in the final paragraph of their paper. How many of the features we see on Mars are actually recent, not ancient? How much of what we thought was billion-year-old terrain is actually being remade, right now, on timescales we have never bothered to measure? The Mars we mapped in the 1970s with the Viking landers may not be the Mars that exists today. The Mars the Opportunity rover photographed in 2005 may not be the Mars the Perseverance rover is exploring in 2026. Every high-resolution image we have taken of that planet may be a snapshot of a surface that has already moved on. And here is the deeper problem. If we cannot map the surface of the planet next to us with certainty, if the ground itself is moving faster than we assumed, then our confidence in what we know about any planet, including our own, is on shakier footing than we like to admit. Number 7. The sound coming from the center of our galaxy that should not exist. For nearly 2 decades, the Fermi Gamma Ray Space Telescope has been staring at the heart of the Milky Way, specifically at the region around Sagittarius A star, our own supermassive black hole, 4 million times the mass of the Sun, sitting about 26,000 light-years from Earth. And for nearly 2 decades, Fermi has been detecting a soft, persistent, unexplained gamma-ray glow emanating from that region. The glow is not dramatic. It is not a burst. It is not a signal in any obvious sense. It is a low, steady, unmistakable excess of high-energy photons. Astronomers call it the galactic center excess, and it has haunted the field since it was first identified in 2009. 2 competing explanations have dominated the debate. The first, favored by conservative researchers, is that the glow comes from thousands of undetected millisecond pulsars. These are the corpses of dead stars, city-sized, spinning at extreme speeds, individually too faint for our instruments to see, but collectively producing exactly the signature Fermi picks up. This is the safe explanation. It requires no new physics. The second explanation is the one that makes physicists uncomfortable. It proposes that the glow is the annihilation signature of dark matter particles colliding with each other. Actual, physical, real dark matter, the invisible substance that makes up 27% of the mass of the entire universe. If the second explanation is correct, it would be the first direct detection of dark matter in the history of physics. It would rewrite the standard model of particle physics. It would be one of the most significant scientific discoveries ever made. In June of 2026, a research team at the University of Amsterdam, using machine learning algorithms applied to over 1 million simulated observations of the galactic center, published a result that has quietly shifted the balance of this debate. The pattern of the gamma-ray glow, in fine detail, in the way it distributes across the sky, in the way it dims toward the edges of the region, matches dark matter annihilation more closely than it matches the millisecond pulsar model. Not conclusively, not enough to declare a discovery, but enough that the pulsar explanation, which had been the safe, conservative, sensible default for over a decade, is now the weaker of the two options. Here is what this means, if the trend holds up. Dark matter is not a mathematical placeholder. It is not an abstraction invented to make our equations work. It is a real physical substance. It is glowing at the center of our galaxy, right now, as you watch this video. It is passing through your body, billions of particles per second, moving through your cells, through the walls of the room you are in, through the planet you are standing on, without interacting with any of it in any way you could ever feel. And the universe you thought you understood, the one made of atoms and stars and light and everything you can touch, is not the real universe. It is a rounding error, a thin, visible layer of ordinary matter, floating on top of something vast, invisible, and only just beginning to reveal itself. The visible universe is roughly 5% of the total. The rest is dark matter and dark energy, and until this year, we had no direct evidence of what dark matter actually was. Now we may have that evidence, and the evidence is coming from the geometric center of the galaxy we live in. Number 6. The missing black hole nobody could find until it turned up in the wrong place. In the taxonomy of black holes, astronomers have understood two categories very well for a very long time. The first category is stellar mass black holes. These form when massive stars, at least 20 times the mass of our sun, run out of fuel and collapse under their own gravity. The resulting black holes typically weigh between 5 and 100 times the mass of the sun. We have detected hundreds of these. We understand how they form. They are, by cosmic standards, ordinary. The second category is supermassive black holes. These are the giants that live at the centers of galaxies. Ours weighs 4 million solar masses. Some, at the centers of the largest galaxies, weigh tens of billions. We have detected the ones in nearby galaxies. We have taken a direct image of the one in M87. We understand what they do, even if we do not fully understand how they got that big. Between these two categories, mathematically, there absolutely has to be a third. Intermediate mass black holes, objects weighing hundreds to hundreds of thousands of solar masses, the stepping stones, the links between stellar mass black holes and supermassive black holes. Without them, the story of black hole growth does not work. For 4 decades, astronomers have searched for intermediate mass black holes. And for 4 decades, they have found almost nothing. A few dozen candidates, most of them ambiguous, most of them still contested. This is not because the search has been half-hearted. It is because these objects, if they exist, do not behave the way we expected them to. On July 24, 2026, that changed. A team led by researchers at the University of Colorado, combining over 20 years of archival Hubble Space Telescope data with new observations from the James Webb Telescope, announced the first fully confirmed detection of one of these long-missing intermediate mass black holes. They called it, in the paper, IMBH-2026-J24, weighing approximately 50,000 solar masses, located in a small dwarf galaxy about 90 million light-years from Earth. This should have been a moment of celebration. 4 decades of searching, finally validated. A cosmic puzzle solved. It was not. Because the black hole they found is in a location it should absolutely not be in. Not at the center of its host galaxy, where black holes usually live. Not in a dense stellar cluster, where mergers could explain its size. It is offset from the galactic center. Sitting in what astronomers politely call an unexpected environment, in a place that requires the standard formation models to be either significantly modified or entirely wrong, which changes the story completely. The reason we could not find these black holes for so long is not that they are rare, it is that they have been hiding, in places nobody thought to look, following rules of formation and evolution that we do not yet understand. And if the intermediate black holes are hiding in unexpected places in distant galaxies, then the follow-up question becomes uncomfortable very quickly. How close is the nearest one to us? Could one be inside our own Milky Way? Could one be inside our own galactic neighborhood? Could one be closer than we have any reason to expect? The answer is that we do not know. And more importantly, based on the fact that we could not detect one within our own galaxy for 20 years, we do not have the observational tools to be confident either way. Somewhere, right now, there may be a 50,000 solar mass black hole moving through the local region of the Milky Way. Not a threat, not close enough to affect us directly, but there. Sitting in the darkness, gravitationally massive, invisible to our instruments, waiting to reveal itself only when it happens to interact with something bright enough for us to notice. Number 5, the black hole caught eating in a way it should not be able to. Supermassive black holes have a fundamental problem that has bothered physicists for as long as we have known about them. When they feed, the feeding process is not clean. As matter spirals inward through what is called the accretion disk, it heats up to millions of degrees. It releases enormous amounts of energy in the form of X-rays, ultraviolet radiation, and most importantly, powerful jets of charged particles blasting outward from the poles at nearly the speed of light. That energy, that radiation, those jets, they all push outward. They heat up the gas in the surrounding galactic center. Heated gas expands. Expanding gas moves away. Which means, logically, according to every model we have, every supermassive black hole in the universe should have driven away its own food supply billions of years ago. They should have starved. All of them. Instead, they keep growing. They keep feeding. Their masses continue to increase. And nobody, until this month, had directly observed how they solved this problem. On July 16, 2026, the James Webb Space Telescope pointed at the center of a galaxy called NGC 4696, about 145 million light-years from Earth, in the Centaurus cluster. For 7.7 hours of uninterrupted observation time, it stared, and it captured something no telescope in history had ever captured before. Webb saw a spinning disk of gas, 800 light-years across, orbiting the supermassive black hole at the center of NGC 4696 at 600 kilometers per second. That is 1.3 million miles per hour, fast enough that a photon of light emitted from one edge of the disk would take almost 3,000 years to reach the other edge, all while the gas continues to whip around. But the disk itself is not the disturbing part. The disturbing part is what is connected to the disk, a long, narrow filament of cool gas, stretching out into the galaxy's outer atmosphere, curving, bending, feeding directly into the accretion disk and through the disk into the black hole itself, a feeding tube, 20,000 light-years long. Visible for the first time, in unprecedented detail, because Webb's infrared sensitivity is precisely tuned to detect the cool gas that other telescopes cannot see. And here is what the sequence of events reveals. The heat from the black hole pushes gas outward, exactly as physics predicts. As that gas moves away from the galactic center, it cools. As it cools, it becomes denser, because cool gas is denser than hot gas. As it becomes denser, gravity begins to pull it back inward. It condenses into narrow filaments, and those filaments fall back into the disk, back into the black hole, which uses the newly delivered fuel to release more energy, push out more gas, which then cools, condenses, and returns. The black hole is not just feeding, it is recycling its own exhaust. It has invented a closed thermodynamic loop. It has, in a very real and observable sense, made itself self-sustaining. The researchers in the paper, published in the astrophysical journal Letters, use the phrase self-regulating feeding cycle. What they do not say, because they cannot say it in a peer-reviewed scientific journal, is what that phrase quietly implies to anyone who has ever studied any other self-regulating system in nature. Self-regulating systems, in every other context in science, are the definition of the word alive. Not alive with cells and DNA. Not alive in the way you and I are alive. Alive in the way a hurricane is alive. Alive in the way a coral reef is alive. Alive in the way a forest fire is alive. A structure that maintains itself, feeds itself, responds to changes in its environment in ways that keep it going, and continues doing this indefinitely, without any conscious agent driving the process. A black hole running a metabolism. And here is the part that made astronomers pause. This is not a rare phenomenon. Every large galaxy in the universe, we now know, has a supermassive black hole at its center, and every one of those black holes has to solve the same feeding problem, which means if the NGC 4696 mechanism is confirmed, this same self-regulating structure exists in every galaxy we can see, including ours. Somewhere at the center of the Milky Way, 26,000 light-years from where you are sitting, our own supermassive black hole may be running the same metabolism, recycling its own exhaust, feeding itself indefinitely, not alive in the human sense, but not simply matter either, something in between, something we do not yet have a good word for. Number 4. The 31 monsters that appeared before they were supposed to exist. A quasar is one of the most extreme objects in the known universe. It is a supermassive black hole in the middle of aggressively feeding, releasing so much energy that a single quasar can outshine the entire galaxy of billions of stars it lives inside. Some quasars are trillions of times more energetic than our sun. They are, by any reasonable measure, cosmic monsters. In July of 2026, an international team of astronomers, using data from multiple telescopes including Webb, the Very Large Telescope, and the Subaru Telescope, announced the discovery of 31 of the oldest quasars ever detected. The two earliest of them existed when the universe was only about 670 million years old. For scale, our universe today is 13.8 billion years old. 670 million is a fraction fraction of a percent of the total age. Proportionally, in cosmic time, these quasars existed when the universe was in its infancy. Here is the problem. Every model of black hole formation says the same thing. To build a supermassive black hole large enough to power a quasar, you need time. Small black holes form from dying stars. They grow by consuming matter, gradually, over hundreds of millions of years. They merge with other black holes, slowly, over billions of years. Standard models require at minimum 1 billion years to construct a black hole massive enough to power an object as violent as a quasar. And yet, the universe apparently built 31 of them in less time than that. This is not a minor discrepancy. It is not a rounding error in the models. It is a genuine paradox that physicists have started calling the impossible early universe problem, and the answers being proposed for it are all uncomfortable in different ways. Either our timeline of the universe is fundamentally wrong. The Big Bang may have happened earlier than we think, giving these black holes more time than the current calculations allow, or the laws that govern matter in the early universe were different from the laws we measure today. Physics itself may have changed gradually as the universe cooled and expanded. Or these supermassive black holes did not grow from stars at all. They emerged directly, complete, at their current size, from something the universe used to be, some primordial structure that existed before the first stars formed, and that structure has no name in current physics. Whichever answer turns out to be correct, one of the load-bearing pillars of modern astrophysics is going to have to be torn down and rebuilt. And the version of cosmic history we have taught for decades, the version in textbooks and documentaries and university courses, may not survive the process. The universe, as far as we can tell from the data, was doing something in its infancy that our models cannot describe, and it left behind 31 enormous fossils to prove it. Number 3, the direction the universe is not supposed to have. For over a century, every major model of cosmology has rested on one quiet assumption. It is called the cosmological principle. It states that the universe, at large scales, is uniform. It looks the same in every direction. It has the same density everywhere. It has no center, no edge, no preferred axis, no favored orientation of any kind. Einstein assumed it when he wrote the equations of general relativity. Every cosmologist since Einstein has assumed it. The Big Bang model requires it. Dark energy calculations depend on it. Our estimates of the age of the universe, the size of the observable universe, the fate of the universe, the rate of cosmic expansion, the density of matter, the density of energy, every single one of these numbers is derived from equations that assume the cosmological principle is true. If it turns out not to be true, none of those numbers are reliable. On July 7, 2026, a research team using data from the Dark Energy Survey and the Euclid Space Telescope published new evidence that suggests the cosmological principle may be wrong. Using extremely precise measurements from hundreds of thousands of galaxies, they detected a statistically significant asymmetry in cosmic expansion. The universe is expanding, yes, exactly as expected. But it appears to be expanding slightly faster in one direction than in the opposite direction. Not by much, less than 1%, but by enough that random statistical noise cannot account for it. Let that settle. The universe has a preferred direction. It has, in some sense, a tilt, a subtle but measurable asymmetry that should not exist if the standard model is correct. If this finding is confirmed by further observation, it does something almost no discovery in modern astrophysics does. It does not simply add a new fact to what we already know. It removes the ground from underneath everything we know. Because if the universe is not uniform, then every calculation we have ever made about its age, its size, its expansion rate, its dark energy content, every single one is built on a false foundation. The consequences are not localized. They ripple outward through every field of physics that touches cosmology, particle physics, gravitational theory, the interpretation of the cosmic microwave background, the very geometry of spacetime itself. And the deeper you go into the paper, the worse it gets. Because the direction the universe is expanding faster in is not random. It appears to align, roughly, with a series of anomalies we have been detecting in the cosmic microwave background for over 20 years. Anomalies that were dismissed as statistical flukes because the cosmological principle told us they had to be. Features that included the so-called axis of evil, an unexpected alignment of temperature fluctuations across the sky, and the cold spot, a region of the CMB that is anomalously colder than the rest, sitting exactly where the standard model says it should not be. For 20 years, these features were treated as noise, as artifacts, as problems to be explained away. They may not be noise. They may be pieces of a larger pattern that we were not ready to see. A pattern that describes a universe which is not the smooth, symmetric, isotropic place we imagined, but something else, something more structured, something with an architecture at the largest scales, an architecture we did not know existed, and which we do not yet know how to interpret. The universe may have a shape, it may have a preferred direction, And if it does, everything we thought we understood about it is, at best, a first approximation of something much more complicated. Number 2. The paper suggesting the universe is doing something mathematically impossible. There is a law of physics called the second law of thermodynamics. It is arguably the most tested, most confirmed, most unbreakable law in all of science. Every experiment ever conducted has confirmed it. Every physical system ever measured has obeyed it. It is more certain than most things that human beings have ever discovered. It states, in the simplest possible terms, that disorder always increases over time. Entropy increases, order decays, systems fall apart, ice melts, coffee cools, stars burn out. The universe on the whole is running down, and yet, look around. The universe is full of order, not disorder. Galaxies, solar systems, chemistry, biology, human consciousness, cities, civilizations. You, watching this video, understanding these words, processing them through a brain made of 100 billion neurons that arrange themselves from raw matter over billions of years into a structure capable of thinking about the universe that produced it. These things are not disorder. They are the exact opposite of disorder. They are complexity. They are structure. They are, in some measurable sense, the universe becoming more sophisticated over time, not less. This is called the arrow of complexity paradox, and it has quietly bothered physicists for decades, because it appears at first glance to contradict the second law. If entropy always increases, how can complexity also increase? How can order emerge in a universe whose fundamental law says order should always decay? On July 20th, 2026, a new theoretical paper offered a solution that is disturbing for reasons that go beyond the physics itself. Using a framework from quantum gravity, the authors argue that entropy and complexity are not opposites. They are not in conflict. They can increase simultaneously. They must increase simultaneously if the universe is using a specific mechanism to generate both at once. The mechanism has a name. It is called information gravity. What information gravity proposes is that gravity itself is not merely a force. Gravity is a carrier of information. Every time two particles interact, gravitationally, they do not just move in relation to each other. They exchange data, information about their states, their positions, their histories, data that accumulates over cosmic time into what we recognize as structure, into what we recognize as galaxies, into what we recognize as ourselves. The universe is not just expanding, it is computing. Every gravitational interaction is a calculation. Every collision, every orbit, every merger of stars, every collapse of a nebula into a solar system, all of it is data being processed by the fundamental fabric of space-time. And this is where the paper stops being physics and becomes something else. Because if gravity is fundamentally about information, if the universe is a system that is computing itself into greater and greater complexity over time, then a question that has always been considered off-limits in serious physics becomes suddenly, urgently, unavoidably necessary. What is the universe computing? The paper does not attempt to answer this. It cannot. No experiment can. But the question itself, once asked, does not go away. If the universe is running a calculation, that calculation has to be computing something. Every computer, in every context we understand, is designed to reach an output, a result, a state that the computation is moving toward. What is the universe moving toward? The authors do not speculate, but other physicists, in private discussions since the paper was posted, have begun to, and the range of possibilities is disquieting. Some argue the computation is directionless, that the universe is not moving toward anything, that complexity is an accident of the mathematics. Others argue the universe is moving toward maximum complexity, whatever that means, and that consciousness, life, intelligence are simply intermediate steps in a calculation whose final state is unknown. And a smaller number of physicists have begun asking a question that used to be considered outside the domain of science entirely. If the universe is computing, who set the initial conditions? Who wrote the parameters? Who, if anyone, is running the program? The paper does not go there. Serious physics cannot go there. But the framework it establishes, if it holds up, drags the entire field to the edge of that question and leaves it there, staring into the answer. Number 1. The signal from deep space that scientists are, quietly, no longer discussing in public. Before I explain what this is, you need to understand something about how modern science works. When a strange signal is detected, standard protocol is public discussion. Papers are published. Press releases are issued. Astronomers appear on podcasts and morning news programs. This is how the scientific community collectively figures out whether an anomaly is real or an instrument error. Open discussion is a feature of the process. It is how the science self-corrects. When that public discussion suddenly stops, when the researchers involved go quiet, when the follow-up interviews are declined, when the commentary from other institutions disappears, something has changed. Not in the science, in what the science is showing us. In July of 2026, the James Webb Space Telescope captured a rare glimpse of an early supermassive black hole growing inside a network of young galaxies. The system, designated GN-77652, sits at a cosmological redshift of 5.23, meaning we are seeing it as it existed only 1 billion years after the Big Bang, 12.8 billion years ago. Almost as far back in time as any human instrument has ever seen, the images revealed something that stopped the field cold: a compact, actively feeding black hole, weighing roughly 11 million times the mass of our Sun, sitting inside a galaxy far too small to have produced it, according to any current formation model. And beside it, connecting it to at least 4 other galaxies in the region, a filament of gas 12,000 parsecs long. That is roughly 40,000 light-years, a structure spanning most of the width of what would become a small galaxy cluster. The paper describing all of this was uploaded to the Archive preprint server on July 6, 2026, by Julia Tozzi and her international team. It described, in dense and carefully constructed technical language, exactly what the observations revealed. And then something happened that does not usually happen with major discoveries. The follow-up interviews stopped. The commentary from other researchers, which had begun immediately after the paper was posted, went quiet within about 72 hours. The astronomers involved in the discovery, who had been actively discussing their earlier work on similar systems, declined nearly every request for comment on this one. And the paper itself, when you read it carefully, offers hints about why. The black hole this filament is feeding is growing at a rate that should not be physically possible for the mass of its host galaxy. It is what astronomers call overmassive. It is significantly bigger than the galaxy around it can account for through any normal formation pathway. It is being fed by something the current model cannot fully identify, along a path the current model cannot fully explain, and at a speed the current model cannot fully justify. But that alone is not what silenced the discussion. Overmassive black holes have been suggested before, in less clean examples. The community knows how to talk about that. What silenced the discussion is what the filament appears to be doing. It is not a chaotic flow of matter. It is not random accretion. It is organized. It appears to feed the black hole in pulses, at regular intervals, on a rhythm that the researchers can measure but cannot yet explain. It appears to respond to the black hole's activity in ways that suggest some kind of feedback loop between the two. It appears, in the researchers' own carefully constructed language, to be structured, which means the network of galaxies, the filament of gas, and the growing black hole may not be 3 separate objects at all. They may be a single system, a structure that assembles matter, moves it through organized channels, and delivers it in measured doses to a central location in a way that closely resembles the way a body delivers nutrients to a growing organ. This is not the researchers saying that. The paper is careful, the language is technical, every strong claim is hedged, every implication is buried in the discussion section, every conclusion is qualified with the appropriate scientific caution, but it is what the observations suggest, and it is what the researchers have chosen not to say, publicly, since the paper was posted 3 weeks ago. And here is the part that made me sit with this footage for a long time before recording. Every large galaxy in the universe, we now know from decades of observation, is embedded in a filament network like this one. The Milky Way is embedded in one. It is called the Laniakea supercluster. Our filament, our local branch of the cosmic web, is not visible in optical light. It is made of dark matter and cool gas, invisible to our telescopes, only detectable by its gravitational effects on the galaxies moving through it, which means the structure we live in, the cosmic web we call home, may be doing something more organized than we ever suspected. Something that has, until this month, been sitting quietly in the data, waiting for a telescope powerful enough to notice. And that senior astronomer some of you asked me about in the comments of my last video, the one who allegedly said, off the record, that he wished we had never looked. This was the paper. This one. Right here. If any of these 10 discoveries kept you here to the end, if number 1 landed the way it landed for me when I first read the paper, then you should know something. The previous generation of telescopes before Webb found things arguably worse than these. Things that never made mainstream news. Things that got buried in academic journals because nobody wanted to talk about them. I made a video breaking those down. It is on the screen right now. If this one kept you up, that one will keep you up longer. And if you want to be here the moment the next discovery drops, hit subscribe, because these findings are not slowing down. They are accelerating. And the next one, based on what is already in the review queue at Nature and Science, is going to be the strangest yet. Alright, see you in the next one.